In previous videos, we have learned about forward kinematics and inverse kinematics. Remember that forward kinematics is the problem where, given the joint variables, we find the end effector position. In other words, the joint variables are the input, and the end effector position is the output. Inverse kinematics is the opposite problem. In inverse kinematics, the input is the end effector position, and the output is the joint variables. When we've looked at these two problems in the past, we have focused primarily on simple serial manipulators that don't have very many offsets between the joints. We learned a method of doing the forward kinematics in which we draw coordinate frames on each of the joints, and then we find the rotation matrices and displacement vectors that transform one set of coordinates into the next. We then combine the rotation and displacement matrices into the homogeneous transformation matrices. In this set of videos, we're going to go back and look again at the forward kinematics problem, but we're going to learn a slightly different method of doing this than what we learned previously. The method that we are learning today for doing forward kinematics is called the Denavit Hartenberg representation method. The Denavit Hartenberg representation method is a slightly different method of finding the homogeneous transformation matrix, in other words, of doing forward kinematics, that works well in the case where we have manipulators with different kinds of offsets. The method that we used previously for manipulators that do not have offsets will still work for manipulators that do have offsets. The Denavit-Hartenberg method is considered by some to be an easier method when you have manipulators with offsets, and it's considered to be a standard for the more complex manipulators, and so that's why it's a good thing to know if you're going into the robotics field. However, either method will work. In the previous method that we learned for forward kinematics, we did not have to be particularly careful about how we assigned the coordinate axes, but after we had assigned the coordinate axes, the process of finding the homogeneous transformation matrices was a bit complex. With the Denavit-Hartenberg method, this process is reversed in that you must be extremely careful about how you assign coordinate axes, but if you get those axes assigned correctly, then the process of finding the homogeneous transformation matrix is much simpler. In short, if we are very careful about how we assign the coordinate axes to each joint in our manipulator, then we can simplify the forward kinematics, the process of finding the homogeneous transformation matrix, to only 4 parameters. The rest of these videos have 3 parts. One part is the definition of the 4 parameters and how those parameters are used to find the homogeneous transformation matrix. The second part is how to assign the coordinate frames. In that part, I'll give you the rules for how we have to assign coordinate frames, and I'll give you some examples for how we do this correctly. Finally, I'll show some complete examples of the Denavit-Hartenberg method. You can watch these videos in any order, as the individual pieces are independent of one another, although you might want to watch the complete examples last, or perhaps at the beginning and also at the end. There will be several different videos with different examples.